Let's solve this probability problem involving dice rolls and frequency tables. Claire rolls a 6-sided die 16 times and records the results in this frequency table. We can see that some scores occurred with known frequencies, while others are represented by variables p and q. We're also told that the mean score is 3. Let's solve this step by step. First, we know that all frequencies must add up to the total number of rolls, which is 16. So p plus q plus 4 plus 2 plus 0 plus 3 égale 16. Simplifying, we get p plus q equals 7. This is our first equation. Next, since we know the mean is 3, we can use the formula for mean. The sum of each score times its frequency divided by the total frequency. This gives us 1 times p plus 2 times q plus 3 times 4 plus 4 times 2 plus 5 times 0 plus 6 times 3, all divided by 16, equals 3. Let's simplify this equation. Multiply both sides by 16 and simplify the right side. We get p plus 2q plus 12 plus 8 plus 0 plus 18 equals 48. Further simplifying, p plus 2q equals 10. This is our second equation. Now we have a system of two equations, p plus q equals 7 and p plus 2q equals 10. To solve this, let's subtract the first equation from the second. This gives us q equals 3. Substituting back, we get p equals 4. Let's verify our answer by putting these values back in the table. With p equals 4 and q equals 3, we can check that all frequencies sum to 16, and the mean is indeed 3. Finally, for part B, since each score is multiplied by 10, the mean final score will also be multiplied by 10. So the mean final score is 30. Let's solve this logarithm problem step by step. We're given that log base 10 of a equals 1/3, where a is greater than 0. Let's solve part A first. We need to find log base 10 of 1 over a. To solve this, we can use a key logarithm property. The log of a reciprocal equals the negative of the log of the number. Applying this property to our problem, we get log base 10 of 1 over a equals negative log base 10 of a. Since we know log base 10 of a equals 1/3, we can substitute that in. Therefore, log base 10 of 1 over a equals negative 1/3. Now, let's solve part B. We need to find log base 1000 of a. To solve this, we can use the change of base formula, which states that log base b of x equals log base m of x divided by log base m of b. In our case, we want to convert log base 1000 to log base 10. So we'll have log base 1000 of it equals log base 10 of it divided by log base 10 of 1000. We know log base 10 of it is 1/3, and log base 10 of 1000 equals 3, since 1000 is 10 cubed. Now we can substitute these values. Log base 1000 of it equals 1/3 divided by 3. Simplifying this, we get 1/9. Let's summarize our answers. For part A, log base 10 of 1 over a equals negative 1/3. And for part B, log base 1000 of it equals 1/9. Let's solve this circle sector problem step by step. We're given a sector with radius r centimeters, angle theta in radians, a perimeter of 10 centimeters, and an area of 6.25 square centimeters. Let's start by drawing our sector. Here's our circle sector OAB with radius r and angle theta. The perimeter consists of 2 radii and the arc length. Let's write down what we know about the perimeter. The perimeter equals 2 times r for the radii, plus r times theta for the arc length, and this equals 10 centimeters. For the area, we know that the area of a sector is 1/2 r squared times theta, and this equals 6.25 square centimeters. From the perimeter equation, we can solve for theta. We get theta equals 10 minus 2r, all divided by r. Now let's substitute this expression for theta into our area equation. When we do this and simplify, we get 4r cubed minus 20r squared plus 25 equals 0. This is a quadratic equation. Using the quadratic formula, we can solve for r. The only positive solution is r equals 2.5 centimeters. Finally, we can substitute our equals 2.5 back into our equation for theta. This gives us theta equals 2 radians. Therefore, our final answer is that our equals 2.5 centimeters and theta equals 2 radians. Let's solve this problem involving the intersection of trigonometric functions and find the area between them. We have two functions, f of x equals cosine x and g of x equals sine of 2x, where x is between 0 and pi. Let's start by graphing these functions. Here's our coordinate system. First, let's plot f of x equals cosine x in blue, and now g of x equals sine of 2x in red. To find the intersection points, we need to solve the equation cosine x equals sine of 2x. Using the double angle formula, sine of 2x equals 2 sine x cosine x. This gives us the equation cosine x equals 2 sine x cosine x. If cosine x is not 0, we can divide both sides by cosine x to get 1 equals 2 sine x. This means sine x equals 1/2, which gives us x equals pi over 6 or 5 pi over 6. We also know that b is at x equals pi over 2. Now for part B, we need to find the area of region R between the curves from point B to point C. This area is given by the integral from pi over 2 to 5 pi over 6 of cosine x minus sine of 2x dx. When we evaluate this integral, we get sine x plus 1/2 cosine of 2x evaluated from pi over 2 to 5 pi over 6. After calculating and simplifying, we find that the area of region R equals 1/4 square units. In conclusion, we found that the x-coordinates of the intersection points are pi over 6 and 5 pi over 6, and the area of region R is 1/4 square units. Let's solve this problem about geometric sequences step by step. We have a geometric sequence with first term 1 and common ratio 10. Let's start with part A. We need to find an expression for s underscore n in the form a to the n minus 1 over b, where a and b are integers. For a geometric sequence, we can use the formula for the sum of n terms. S underscore n equals a underscore 1 times r to the n minus 1 divided by r minus 1. Let's substitute our values. The first term a underscore 1 is 1 and r is 10. This gives us 10 to the n minus 1 divided by 9. Let's see what this looks like for the first few terms of our sequence. The first term is 1, the second is 10, the third is 100, and so on. Therefore, s underscore 1 equals 1, s underscore 2 equals 11, s underscore 3 equals 111. Now for part B, we need to find the sum of all these s underscore n values from s underscore 1 up to s underscore. Let's call this sum capital sigma of s underscore k from k equals 1 to n. We can substitute our expression for s underscore n that we found in part A. This gives us the sum from k equals 1 to n of 10 to the k minus 1 over 9. We can break this down into two separate sums. One sum for 10 to the k over 9, and another sum for negative 1 over 9. After solving these sums and simplifying, we get our final result. 10 times 10 to the n minus 1 minus 9n, all divided by 81. We can verify this result by plugging in small values of n. For example, when n equals 1, we get our original first term. When n equals 2, we get the sum of s underscore 1 and s underscore 2, and so on. Let's solve this calculus problem involving finding the volume of a solid formed by rotating a region about the x-axis. We're given the function f of x equals the square root of x times sine of x squared, where x is between 0 and square root of pi. Let's start by visualizing the region R that we'll be rotating. Here's our coordinate system, and here's the graph of our function. The region R is bounded by our function above, the x-axis below, and the vertical line at x equals square root of pi over 2. When we rotate this region around the x-axis by 2 pi radians, it forms a three-dimensional solid. Each point on the curve traces out a circle, creating circular cross-sections perpendicular to the x-axis. To find the volume, we'll use the washer method. The volume equals pi times the integral from 0 to square root of pi over 2 of f of x squared dx. Substituting our function, we get pi times the integral of x sine of x squared dx. To solve this, let's use u substitution. Let u equal x squared, then do equals 2x dx. After substitution, our integral becomes pi over 2 times the integral from 0 to pi over 4 of sine u du. This evaluates to pi over 2 times negative cosine u, from 0 to pi over 4. Finally, evaluating this gives us pi times 2 minus square root of 2 all over 4, which is our answer. Let's prove using mathematical induction that the sum of our choose 1 from r equals 1 to n is equal to n plus 1 choose 2. First, let's understand what this means. On the left side, we're summing our choose 1 from r equals 1 to n. Note that our choose 1 is just equal to r itself. Let's start with the base case. When n equals 1, the left side is just 1 choose 1, which equals 1. On the right side, we have 2 choose 2, which also equals 1. So our base case holds. Now for the inductive step, we assume the statement is true for n equals k, meaning the sum from r equals 1 to k of r choose 1 equals k plus 1 choose 2. We need to prove it's true for n equals k plus 1. The left side becomes the sum from r equals 1 to k plus 1 of r choose 1. We can split this into 2 parts. The sum up to k plus 1 choose 1. Using our inductive hypothesis, we can substitute k plus 1 choose 2 for the sum up to k. Remember that k plus 1 choose 1 is just k plus 1. Now let's show this equals k plus 2 choose 2. We can write k plus 2 choose 2 as k plus 2 times k plus 1 divided by 2. Through algebra, we can show these expressions are equal. Therefore, by mathematical induction, we have proven that the sum of our choose 1 from r equals 1 to n equals n plus 1 choose 2 for all positive integers n. Let's solve this problem about finding Maclaurin series expansions step by step. We'll start with part A, finding the first 2 non-zero terms in the Maclaurin series of sine of x squared. First, let's recall the Maclaurin series for sine of x. The series is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial, and so on. To find sine of x squared, we simply substitute x squared for x everywhere in the series. This gives us x squared minus x to the 6th over 6 plus x to the 10th over 120, and so on. For part A, part 2, we need to find sine squared of x squared. We can square our previous result. Let's multiply sine of x squared by itself. Now for part B, we need to find the Maclaurin series of 4x times sine of x squared times cosine of x squared. We can use the double angle formula, which states that sine of 2 theta equals 2 sine theta cosine theta. Using this identity, we can rewrite our expression as 2x sine of 2x squared. Now, we can use our knowledge of the sine series again, but this time with 2x squared as the input. After substituting and multiplying by 2x, we get 4x cubed minus 8x to the 7th over 3 as our first 2 non-zero terms. Let's summarize our results. For sine of x squared, we got x squared minus x to the 6th over 6. For sine squared of x squared, we got x to the 4th minus x to the 8th over 3. And for 4x sine x squared cosine x squared, we got 4x cubed minus 8x to the 7th over 3.